Light is more than just what our eyes perceive. It is a fundamental aspect of the universe, revealing secrets that are otherwise hidden from our senses. It's a form of energy known as electromagnetic radiation, which encompasses a vast range of phenomena beyond visible light. This radiation travels in waves like ripples on a pond, spreading out and carrying energy across the cosmos. These waves come in different sizes, which we call wavelengths. Each wavelength represents a different type of electromagnetic radiation. The entire range of these wavelengths is called the electromagnetic spectrum, which includes everything from radio waves to gamma rays. At one end of this spectrum, we have radio waves, which have the longest wavelengths. These waves can travel great distances and are used for communication. At the other end are gamma rays with incredibly short wavelengths. These rays are highly energetic and can penetrate most materials. Visible light, the kind our eyes can see, occupies a tiny sliver in the middle of this spectrum. This small section is what allows us to perceive the world in color. Each color we see corresponds to a specific wavelength within this sliver. For instance, the color red has a longer wavelength compared to blue. Red has the longest wavelength and violet has the shortest. This range of colors is what makes up the visible spectrum. But the entire spectrum, from radio waves to gamma rays, is crucial for understanding the universe. Each type of wave provides unique information about the cosmos. It's the language the cosmos speaks, and we listen in with telescopes and detectors. By studying these waves, we can uncover the mysteries of the universe and gain a deeper understanding of the cosmos.
Light can act like a wave, spreading out like ripples in a pond. Imagine throwing a stone into a still pond. The ripples that spread out are similar to how light waves propagate through space. This wave-like nature explains how light bends around corners, known as diffraction, and creates interference patterns. When light passes through a small aperture or slits, it spreads out and overlaps, creating patterns of light and dark bands. But light also behaves like a particle. This particle aspect is evident in phenomena like the photoelectric effect, where light knocks electrons off a material. This dual nature, known as wave-particle duality, is one of the most intriguing aspects of quantum mechanics. It challenges our classical understanding of physics, and shows that light doesn't fit neatly into one category. When light acts like a particle, we call these particles photons. Photons are the fundamental units or quanta of light. Photons are packets of energy. Each photon carries a specific amount of energy, which is determined by its frequency. The amount of energy a photon carries depends on its wavelength. Higher frequency light, like ultraviolet, carries more energy than lower frequency light, like infrared. Shorter wavelengths, like those of gamma rays, pack more energy. These high-energy photons can penetrate materials and are used in medical imaging. Longer wavelengths, like those of radio waves, carry less. These low-energy photons are used in communication technologies like radio and television. Think of it like this. Imagine a wave in the ocean. The wave itself represents the wave nature of light, spreading out and moving through space. The wave itself is like the wave nature of light. It moves continuously and can interfere with other waves. But within that wave, there might be a surfer riding along. This surfer represents the particle nature of light. The surfer is like the particle nature of light, carrying energy with it. Just as the surfer moves with the wave, photons travel with the light wave, each carrying a discrete packet of energy. One of the most fundamental constants in physics is the speed of light. In the vacuum of space, light travels at approximately 299,792,458 meters per second. That's incredibly fast. Nothing in the universe can travel faster than light. This speed limit has profound implications for our understanding of the cosmos. For instance, when we look at distant stars and galaxies, we're actually seeing them as they were in the past. This is because the light from those objects takes time to reach us. The farther away an object is, the longer it takes for its light to reach us. So we see it as it was further back in time. This concept is crucial for studying the evolution of the universe. Deep within the heart of stars, a process called nuclear fusion takes place. This is the cosmic engine that powers stars and creates light. In nuclear fusion, lighter elements like hydrogen are forced together under immense pressure and temperature to form heavier elements like helium. This process releases an enormous amount of energy, some of which is carried away by photons, the particles of light. These photons then begin their long journey from the star's core to its surface. Imagine a bustling city at night, with lights shining from every window. Each of those lights represents a photon, a tiny packet of energy, escaping from the star's core. Section 5. Cosmic Messengers, Redshifts and Blueshifts. In this section we will explore how the light from distant galaxies serves as a cosmic messenger, revealing the secrets of the universe's expansion and motion. Light from distant galaxies can tell us a lot about the universe's expansion. By studying the light that reaches us, astronomers can determine not only the distance of these galaxies, but also their speed and direction of movement. As light waves travel through space, their wavelengths can stretch or compress depending on the motion of the source emitting the light. This phenomenon is similar to how sound waves behave when a source moves relative to an observer. When a galaxy is moving away from us, its light waves are stretched, shifting towards the red end of the spectrum. This is called redshift. The greater the redshift, the faster the galaxy is receding from us. Conversely, when a galaxy is moving towards us, its light waves are compressed, shifting towards the blue end of the spectrum. This is called blueshift. The amount of blueshift indicates how quickly the galaxy is approaching us. Think of a siren approaching an observer. The sound waves compress as the siren gets closer, resulting in a higher pitch. As the siren moves closer, the sound waves compress, resulting in a higher pitch. This is known as the Doppler effect, and it applies to both sound and light waves. As the siren moves away, the sound waves stretch, resulting in a lower pitch. Similarly, light waves stretch when a galaxy moves away from us, causing redshift. The amount of redshift or blueshift tells us how fast a galaxy is moving relative to us. By measuring these shifts, astronomers can map the motion of galaxies and understand the dynamics of the universe. This information is crucial for understanding the large-scale structure and evolution of the universe. It helps us piece together the history of cosmic expansion and the forces shaping the cosmos. Section 6. Echoes of the Big Bang. The cosmic microwave background radiation, or CMB, is a faint afterglow of the Big Bang, the event that marked the beginning of our universe. This radiation permeates all of space and can be detected in every direction. The CMB provides a snapshot of the universe as it was just 380,000 years after the Big Bang. It's a treasure trove of information about the early universe's conditions, such as its temperature and composition. Think of an echo bouncing off the walls of a canyon. The echo carries information about the shape and size of the canyon. Similarly, the CMB carries information about the early universe. Section 7. Light and Life, an Intimate Connection. Light is essential for life on Earth. Plants, algae, and some bacteria use sunlight to produce energy through photosynthesis. This process converts light energy into chemical energy, which is stored in the bonds of sugar molecules. This stored energy is the foundation of most food chains on Earth. Without light, life as we know it wouldn't exist. Beyond Earth, the search for extraterrestrial life often focuses on planets located in the habitable zones of stars. These are regions around a star where temperatures are just right for liquid water to exist on a planet's surface. Liquid water is thought to be essential for life as we know it. The presence of light and liquid water on other planets could indicate potential habitability. Section 8. Trapped by Gravity, the Mystery of Black Holes. Black holes are among the most enigmatic objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. This extreme gravity arises from the collapse of massive stars at the end of their lives. The star's core collapses to an infinitely small point called a singularity. Surrounding the singularity is an invisible boundary called the event horizon. Anything that crosses the event horizon, including light, is trapped forever. Imagine a waterfall. The point of no return where the water plunges over the edge is like the event horizon of a black hole. Section 9. Cosmic Lenses bending light's path. Gravity doesn't only affect objects with mass, it also warps the fabric of space-time itself. This warping can bend the path of light as it travels through the universe, a phenomenon known as gravitational lensing. Massive objects like galaxies and clusters of galaxies can act as cosmic lenses, magnifying and distorting the light from objects behind them. This lensing effect can create multiple images of the same background object, forming arcs, rings, or even cross-shaped patterns in the sky. Think of a magnifying glass. It bends light to enlarge the appearance of objects. Similarly, massive objects in space can bend light, magnifying and distorting the appearance of distant objects. Section 10. Illuminating the universe. Light is our guide. Light is our primary tool for exploring the vast expanse of the universe. By studying the light emitted, absorbed, or scattered by celestial objects, we can unravel the mysteries of the cosmos. From the birth and death of stars to the expansion of the universe and the search for extraterrestrial life, light illuminates our understanding of the cosmos. Telescopes on Earth and in space capture light from distant galaxies, revealing their composition, motion, and evolution. Spectroscopy, the study of the interaction between matter and electromagnetic radiation, allows us to determine the chemical makeup of stars and planets. As we continue to develop more sophisticated telescopes and instruments, our understanding of the universe will continue to grow, guided by the cosmic messenger of light.